You know, I kind of disagree.
I've never seen the Oscars.
Does that make sense?
Yeah,
No,
seems like a different
Yeah. Or the Emmys, or any of those
Oscars.
award shows I've never seen.
Yeah, it's this Sunday,
I think
the
we did it a little
24th.
different, but I think it's still the same.
Well,
Our number 3.
Hey, Black Panther's in it.
it's not a bumper year for good movies this year.
Normally they have like
All right, let's look at our.
At where?
this like the Oscar party that he does yet. I don't think he's doing it this year.
You guys
I
never
heard not anything about it. Well, it was like last year. It's happened. Usually announced.
Same mechanism every time. Let's.
There you go. Didn't want to run over it with them. What the hell?
Yeah, what's the door?
We just give it a finger.
That's only 20. And you need a 60 and a 40. And it's only 20. I'll tell you right after this.
The 40 plus the 20. Like,
Yeah, like it's just gonna be a dinner.
I know what
figure
you
it out now.
okay, you can explain to me after.
I'll tell you after.
Take a lot of time. So.
Nucleophilic addition. Okay? We've seen this. Hydroxide. And it made a geminal diol. Okay. Did we do another example after this?
Yeah.
I thought we did. I thought you said hydroxide.
We did like a chiral molecule.
Oh yeah. Okay. So this is where we ended. It's the same mechanism, but we're going to adapt it. Over the course of today, we're going to do a variation on this, where we tone down the strength of the nucleophile. So everything that's been seen up to this point has the has the negatively charged nucleophile be out front. And then, because it's an addition, not a substitution, I'm left with the negative charge in my molecule, which I then take care of with this thing that we call acid worker. And the site for the reaction for attack by nucleophiles is that electron deficient carbon. So we always end with the new group, the new substituent, being on the same carbon as the carbons are now holding onto this alcohol group. All right, so we made a geminal diol where both alcohols in that diol were on the same carbon. And this is an ether alcohol hybrid. It is part alcohol, part ether. And they have a name. Technically, let's go all the way to here. If I had a geminal diether that has a hydrogen on that central carbon, then this is an acetal. If there is no hydrogen on that central carbon, this is a ketal. If I've only progressed part way to my reaction and I have something that is part ether, part alcohol, and came from the ketal, then it is a hemiacetal, and this is a hemiacetal. So this right here that we've made in this reaction is a hemiacetal. And I am told, although I will believe it when I see it, that in the future ketals are going to be called acetals because they don't really need their own name. That's a hemiacetal. Has anybody in the room ever heard the word hemiacetal before? Biologically important. Very, very important in biology. In carbohydrate chemistry, we will be seeing hemiacetals later. And you must be able to recognize the carbon with two oxygens, one of which is an alcohol and the other one is a carbon to oxygen. It's a carbon making it an ether. If you can spot in the big ugly molecule the carbon that is holding on to two oxygens, that's the special position. Very, very important in carbohydrates. All right, so this is nucleophilic additions to carbonyls, but then in parentheses, using strong nucleophiles. Okay. Let's use a few more strong ones. What else have we got that is a strong nucleophile? Something not particularly big and with a negative charge. Methoxide. I just erased that one, it was already on the board.
Chloride.
No. No. Chloride is weak.
Okay, what about amide?
It's got so it's not a good base. Amide's a really good one. So let's go through this again. Let's have some groups be here. The simpler you make it now, the more problematic it is for you later on when the exam question doesn't have the simplest molecules on the test. What goes here? What would Dan want?
Methyl.
Dan's not getting his method.
And ethyl.
They're just R groups. They just carry through. They don't participate in the reaction until a couple of chapters from now. Step 1 is the addition of the nucleophile. Step 2 is the acid workup. Let's do it again. Powerful nucleophile, powerful nucleophile that delivers to me something useful for my organic reaction. Something that I don't see a lot of. What if they use a Grignard reagent? Now, I can add an additional carbon. Alkylation by Grignard or other alkylating agents makes you an alcohol. And ketone plus Grignard. What kind of alcohol is that?
Phenol?
Who?
Is it phenol or no?
Oh, no.
Oh.
No, the phenol has the OH actually on the ring.
Oh, okay.
What classification of alcohol is this? What flavor is it?
Like tertiary.
Tertiary alcohol. Can you see what it would be if instead of starting with a ketone, we started with an aldehyde? What would it be then?
Secondary.
Secondary alcohol. Ketones versus aldehydes. All right. This is a ketone because it has carbons on both sides of the carbonyl. If I swap out the methyl for a hydrogen, then my carbon is only bonded to two other carbons. It's now a secondary alcohol. There is one more powerful nucleophile that we have to address. nucleophile is H minus. This is a hydride. And when we look at what hydride does, go ahead and take the electrons from the bond. So you can cheat and just go H minus does this. That's the way I learned it. It's a little bit cheap. To do it the correct way, you take the electrons from the bond between the boron and the hydrogen, and you deliver them to the carbon. By reactants, look at this carbon. It has no bonds to hydrogen, but it has 2 bonds to oxygen. The product's not finished yet, it's going to be finished soon, has 1 bond to oxygen and 1 bond to hydrogen. So under our very old definition of what oxidation is and what reduction is, this is reduced. Because oxidation is an increase in number of bonds to oxygen and a decrease in number of bonds to hydrogen. And reduction is an increase in number of bonds to hydrogen and a decrease in bonds to oxygen. So my molecule has now less bonds to oxygen and more bonds to hydrogen. So it has been reduced. H minus is tiny and negative. It's very, very powerful. And we have to follow it up with step 2 for the acid workup. But step 1 is one of our hydride reducing agents, and we'll talk about these in a second. Okay, is this a ketone or an aldehyde?
Ketone.
It's a ketone. And if ketones undergo reaction with H minus followed by H plus, they make this alcohol. What kind of alcohol is that?
Secondary.
Secondary alcohol. Can you imagine what an aldehyde would do? Let's not imagine. What's the red? That's what an aldehyde would do. I replace the methyls with hydrogens. Aldehyde interacts, the reaction is exactly the same. These groups have not participated yet. Picks up the nucleophile, which is an H minus, and then undergoes acid workup and makes an alcohol. But this is now a primary alcohol. So ketones undergo reduction to make secondary alcohols. Aldehydes make primary alcohols. Okay, let's take a look at this reducing agent. So one thing that we could write just in general, square brackets with a capital R in it means reducing agent. And a reducing agent is something that itself is very easily oxidized, and therefore it reduces its surroundings. So oxidation is the loss of electrons. Reduction is the gain of electrons. Can we see the gain of electrons? Not really. But we can see loss of bonds to oxygen and gain of bonds to hydrogen. That's what a reducing agent is going to cause. All right. Do we know the names of any reducing agents? We do, but I think what we've done mostly is a mix of heterogeneous and homogeneous ones. We haven't seen any of these. These are all solution reducing agents that's going to come up. So we've seen nickel with adsorbed hydrogen. We've seen platinum with adsorbed hydrogen. We've seen palladium and intercalated into graphite with adsorbed hydrogen. These are heterogeneous, and we've used those for a few things. And we've seen zinc. So we've seen metals in combination with acid. Zinc amalgam in acid is the Clemenson, and we've seen tin and hydrochloric acid. There's another category, and those categories are based around group 3. Group 13 if you're an inorganic chemist. Let's look at boron, because there's a boron here. Boron is in group 3. How many valence electrons does it have?
3.
There's 3 valence electrons because it's in group 3. It's grouped into group 3 because it has 3 valence electrons. Let's surround that boron with hydrogens, so it's now saturated. This is now a little molecule called borane. Borane only has 6 valence electrons in its covalency. So it's electron deficient. It's electron deficient. But it's the little molecule that could, and it's going to steal electrons from wherever it can find them. And it's going to accept a pair of electrons from something else. It's going to find a source of hydrogen somewhere, and it's going to accept 2 electrons in a coordinate covalent bond, a dative bond, in which both of the electrons come from the same source. So a covalent bond is 2 electrons shared between 2 atoms, and we're used to seeing that be an electron here and an electron there. 2 electrons shared between 2 atoms. But it could be 2 electrons from here shared between 2 atoms. But hydrogen's in group 1. Hydrogen only has 1 electron. hydrogen is attached to itself, I have 2 electrons shared between those 2 atoms. If I manage to split that bond unevenly, I have the hydrogen atom in the middle, I have the hydronium ion that has no electrons at all, and then I have hydride, which has 2 electrons. So I just do the heterolysis on a molecule of H2. I take the hydride and I give both of those electrons to here. This now makes this tetrahedral, and there is a negative charge in there somewhere. So I'm going to counterbalance that with the sodium. And the way that I make this split is I take the hydrogen and I treat it with sodium, and sodium is interchangeable with hydrogen because they're both in group 1. But sodium doesn't want its electrons. It wants to give its electrons away. Hydrogen, top of the group, covalent. Sodium, ionic. So if I can find a molecule and then change out a hydrogen for a sodium, I make sodium hydride. Then I can take this boron as a borane and make sodium borohydride. Aluminum does exactly the same thing, only better. And we may use the lithium salts of this. And we make lithium aluminum hydride. Now, sodium borohydride and lithium aluminum hydride are not the correct names for these molecules, but they're the names that are widely used. And in fact, the correct names of these molecules is also wrong. So we're kind of stuck. The correct name would be tetrahydridolithium aluminate, which is wrong because 8 at the end of a word means contains oxygen, and there is no oxygen in aluminate. So there's no point in me telling you what the correct name is, only to have it be proved wrong at some point in the future. All right, these 2 are our new reducing agents, and this one is very strong, and it reduces everything. And this one is not so strong. And it reduces aldehydes and ketones. Oops. We're going to learn about what the everything in the statement that lithium aluminum hydride reduces everything. We're going to figure out what the everything in that statement is later. Okay. it is possible to do our nucleophilic additions with nucleophiles that are not so strong. But we're not going to be allowed to do them the same way. We're going to show you addition of water instead of addition of hydroxide, and addition of alcohol instead of addition of methoxide, and addition of amines instead of amide. And that's it, because I don't have any analog for H- or Grignard's CH3-, whatever you call that. So here we go. I'm going to add H2O instead of OH-. So in the past, we had the nucleophile be in the very, very first step. I have something negative. I have an electron deficient carbon, and the strong nucleophile just moves in and adds. Here, something else. Here's my H2O. There's my ethanol. This doesn't happen. Doesn't happen. Here's why. We learned very early on when we were looking at reactions that the incoming nucleophile has to be a stronger base than the leaving group. Now there's no leaving group here because these are additions, but the concept is still the same. But what is the basicity of that lone pair of electrons versus what is the basicity of that lone pair of electrons? Because there's a lone pair of electrons right there, one of which doesn't belong to the oxygen, so there's a negative charge. This is a much more powerful base than this. And the ant does not knock down the building. Okay. This does not have enough power to make that happen. So my reaction doesn't work. But of course it does work because we've given it a title. Plus, I gave it a subtitle. The title is that this is going to be a nucleophilic addition with a weak nucleophile, and then I told you specifically which one I'm going to use. What's the trick? And it is a trick. What do you do to oxygens that won't behave, that won't do what it is that you want them to do? You protonate. So our first step is what we did in the last set of reactions as the last step. You add the acid up front here. One is you protonate. And now I'm going to have a completely different outcome. If I protonate this ketone or aldehyde, now when I attack the carbon, and breaks the pi components of this bond, it doesn't leave a negative charge behind. So, our important thing right here is that these reactions with the weak nucleophiles are acid-catalyzed. They cannot progress unless you have protonated the oxygen. All right. That oxygen is protonated. That pi bond that was in here was always the weakest bond in this molecule, and it still is. But now, when it breaks, it breaks to a single bonded carbon and an oxygen with 2 bonds. So there's no negative charge up here. There's no strong base here, which means I don't need a powerful nucleophile as the driving force to make this happen. And look, my arrows changed. My arrows are no longer arrows that go from left to right. They are now arrows that open up the possibility that everything I write down is in equilibrium. In order to make that bond break, here you go, from the lone pair of electrons to the electron deficient carbon, break the weakest bond, push the electrons towards the positive, from here to here to here. That oxygen now has a positive charge. And I can get rid of it, that positive charge, just by allowing a proton to float back out of solution, sacrifice the electrons that are in that bond. Oh, and look what I've made. I've made a channel dial. Okay, lots to talk about here. Lots and lots and lots and lots to talk about. I have a weak nucleophile. I only use equilibrium arrows now because there is no driving force. Nucleophiles, bases, make bonds. Strong bases, strong nucleophiles make strong bonds. Weak nucleophiles and weak bases make weak bonds. There's no negative here, so this is not a strong nucleophile. All you need to be in a nucleophile is the lone pair of electrons. So I don't have something driving the reaction forward. All of these steps are going to be in equilibrium. Because the reaction is acid-catalyzed, plus goes into my reaction as the very, very first thing, which means I am not allowed to have any negative charges anywhere in this mechanism. Cannot have them. Only positive charges in an acid-catalyzed mechanism. Only positive charges. And then the very, very last thing, and I'm using the word last loosely because we're not done. Acid goes in at the beginning. Acid comes out at the end. The reaction is not possible without the H+, but the H+ is not consumed. Therefore, the H+ is a catalyst. The catalyst is something that you must have, must be present for the reaction to work, but is not required or consumed by the reaction. Okay, and I make my geminal diol. Let's do it again. To use methanol instead of methoxide. And everything is exactly the same, except my product is no longer geminal diol. It's a hemiacetal. It's halfway to an acetal. It's not an acetal. An acetal would have two ether groups. This is halfway. It's a hemiacetal, which is kind of bothering me. Because if it's halfway to something, then we should just do it. We've got 5 minutes. We've got 4 minutes and 45 seconds to get to the acetal. And here's how it happens. Okay. Every single step of the mechanism. Find the nucleophile. Find the electrophile. Let the nucleophile reach out to the electrophile, rationalize where your charges are. Find the nucleophile, find the electrophile, push the arrows, rationalize what you've got. Now, this is where I am. That's an electrophile. It's an H+. It's an acid. I have 4 bases in solution. I've got this lone pair of electrons, I've got that lone pair of electrons, I've got this lone pair of electrons, I've got that lone pair of electrons. Watch very, very carefully. Am I allowed to do that? Is that possible?
You already did it.
Yes, it's possible. I've already described it. It's the backwards arrow here. So if that's possible, then this is possible. Already described it because those two lone pairs are the same as each other. And if they are possible, is it any different than doing that? Yes. Yes, it is. What am I about to make?
Water.
I'm about to make a water. And what does planet Earth love above everything else? Dinitrogen and water. It loves those two things. Let's go make some. I have now made a leaving group. There's a leaving group in my molecule for the very first time. It's right there. H2O. It wants to go. How am I going to make it go?
Between a carbon and an oxygen.
You mumbled, but I think you're saying that.
Yeah.
And this is going to make something that looks crazy, but isn't, because you've already written it down. It's already been on the board once. There's my water. Wait, bye to it. It's gone. I have a carbon to oxygen strange little molecule. It's right there. Difference being that this is now a methyl instead of a hydrogen. But nobody said, wait a minute, that's ridiculous. You've got 2 bonds to an oxygen and a positive on it. Stop. Explain what you're doing. We all accepted it when I wrote it the first time, so you should accept it now. I'm going to make that positive go away. Going to make that positive go away. Here's how I do it. See that lone pair of electrons on this water? If I attacked the carbon, it would go back where it came from. If I did this, the reaction would go backwards. So I know that that's possible. But instead, what I'm going to use is a second molecule of alcohol. Nobody said I had a limited amount of alcohol. Second molecule. Positive charge just went away. It went away on one side and came back on the other. And now I just do this. And with a whole 20 seconds left in the lecture, we have made our acetal. And shown that that step is also catalytic. So I need 2 molecules of alcohol to make the acetal, 1 molecule of alcohol to make the hemiacetal. And the reaction proves to me at the very, very end that it's catalytic by giving me back the H+. We'll see you on Monday. Something has gone wrong. The NMR exercise is now past due. You haven't turned it in because presumably you don't know how to complete it. And yet, nobody has asked me how to complete it. The first one of those infractions is forgivable. The second one doesn't make any sense. Yeah, I didn't turn in my homework because I'm having a hard time. Okay. Ask.